Ladies and gentlemen, it's a real pleasure to speak before you on my favorite subject, which is Mother Earth, and especially in this incredible environment where now we have digital data, not only in the 3 dimensions. I'm going to talk about the 4th dimension, because for us as Earth scientists, the 4th dimension, time, is paramount. So why New Zealand, and what's so special about it? Let's take a God's eye view. It's formed on the plate boundary between the Australian Pacific plates, 2 mighty plates in collision with each other, and hence we have the volcanoes, the Tonga-Kermadec Trench, the Southern Alps, and the active landscape that we have today. So it's a country of active landscapes. Everything's moving. And I'll show you towards the end of my talk that there's movement that you're not even aware of, but it's right underneath your feet. And it's a country of incredibly diverse geology, and of course a country of earthquakes and volcanoes. And what's most important, it's a country that is between 95 and 90% underwater. So it's a huge, huge submarine continent, but we live on this tiny upper 5%. And the challenge for us is to really to digitize it all, everything. So it's accessible to you, the government, our colleagues around the world, and then, of course, distribute it. Brief note about GNS Science. What are we? We're the nation's Earth Sciences Institute. We do the mapping of everything to do with sciences. And we have 400 staff. Out of those, over 300 PhDs. So we're by far the biggest employer of Earth Sciences in New Zealand. I'm not going to go through the details here, but what I wanted to show you was the incredible diversity of activities. We go from geological resources, from past climates, paleodiversity, hydrocarbons, CO2 sequestration, geothermal power, minerals, geomicrobiology, ocean exploration, and gas hydrates. And then, of course, the natural hazards, origin of New Zealand's crust, spatial data on mapping spatial data, tectonic deformation, geohazards monitoring, of course, earthquake processes, volcanoes, landslides, tsunamis, and hazards. And then we have our lab environment in which we use isotopes for our purposes. Yes, we do have a nuclear sciences organization, but it's not the nuclear that you're thinking of. It's using isotopes for different purposes. Radiocarbon dating and water dating, groundwater, soil carbon cycling, and we do have a fantastic accelerator mass spectrometer. So it's not a CERN, but it's essentially does the same work as a CERN, but it would fit into this hole. It's not 100 kilometers in diameter. And we use it radiocarbon and beryllium dating purposes. Now, in a distribution map, I'm not going to give you the details of this, but these are all the components of GNS, situated between geology on your right, geophysics, and geochemistry. And if you can imagine, if you're running this institute the way I am, is to ensure that all this data is digital, it's available, it's cross-linked, it's worked around the world and through the government. It's quite a challenge for us. And we've actually met it, and that's what my talk is all about. First of all, geographic context. Here is New Zealand. And as you can see, the beige-colored terrain around New Zealand, that's a sunken continent. That's part of the old Gondwana land. We call it Zealandia. And the whole area occupies is the size of Australia, but it's largely underwater. So how do we deal with this, and what's it in for us? Now, especially for us, in GNS, the government has told us that we need new revenue streams, that the dairy industry is maxed out, it's plateaued out. What do we do? What can we produce for the country that'll allow us to stop this debt? We're borrowing about $250 million a week. And how do we do that? Well, the avenue, of course, is oil and gas. And we're endowed, if you look at all those brown-colored areas, those are the oil prospective basins around New Zealand. It's a huge challenge to even, as we do, advise the government on what's there and advise them on the possibilities and probabilities of oil. So that's one of our missions. It's a huge mission. And again, what form do we produce it in? It's all digital. I've drawn from the previous talk, Mark Rattenbury, who's our specialist in geospatial mapping. So I'm going to use some of his slides to illustrate as to how we're going about meeting these needs. First of all, New Zealand geology. Then geology of the substratum. And here is a diagram of Christchurch with the geological strata below it. And that's a geological strata. You have water, earthquakes, and you've got liquefaction. So it's absolutely vital information in the rebuild of Christchurch. And we provide it in 3 dimensions, and not only for Christchurch, and now we're looking at other cities as well. So characterizing the New Zealand geology as a whole, what's the geology under our cities? How do we support our infrastructure? What are the important natural resources beyond the cities? And we have to have digital data that originally, as we often talked about, it's in maps, but now it's a 3D geology. And in some areas, it's 4D geology. We'll go to that in a minute. Yes, we share it with the world leaders, and we share our geological information digitally with the world through One Geology, which is an amazing really union of 148 different countries, 148 different geological surveys to produce one result, and that is digital access to all of the geology of all the world. So if you want to drill a well, if you want to rebuild a city, if you want to invest in gold mining or if copper mining, this map will tell you where it is, digitally that is, and it'll be accessible to everyone in the world, free of charge. And surprisingly enough, we've got most of the world covered. North America, much of South America, Australia, South Africa, and recently Russia brought in their data, in China. So we're there. So we're very, very proud of that effort. And I said New Zealand's leading it. We finished mapping the geology in New Zealand, and the map has now been converted to digital format. It's accessible to you if you want to know what sort of rocks are around your favorite areas. And all you have to do is go to our web. So this was called the 1:250,000 geological map of New Zealand. We call it QMap. It's seamless. So each map is adjacent to the other. So it's an effort of many, many years. And I would say, really, the geological map is an effort of 150 years of our existence. And of course, recently, we use modern techniques and modern mapping methods. But 150 years ago, that's when we first developed our first geologic map. And surprisingly enough, luminaries like Hochstetter and so on in the 19th century produced remarkably accurate geological maps of Auckland area and the volcano area, the Southern Alps. But now, it's all digital. To the left, you'll see the geological map, which tells you the ages of the different rocks and the types. In the middle, you'll see the tectonic map, which shows you all the faults and folds and all the tectonics that you're interested in. And bottom right is a detail. Now, Phil Glassy and company, who are in the audience, gave a talk recently about urban geology. What are we doing? Are we getting into the 3-dimensional maps of the urban areas? After the Christchurch earthquake, and I'll show you later on the situation here in Wellington, the demand really for knowledge of what underlies our cities and towns and smaller municipalities now become paramount. For instance, in Christchurch, we have an incredible database of drill holes. You can see all those drill holes there, extending into the sediments. I showed you earlier a map of 3 dimensions of sediments, vital to the rebuild of Christchurch. Well, we've been able to, here's the map again, under the Christchurch Central Business District, take the drill data and build a three-dimensional digital map of the sediments down to 35 or 40 meters. Absolutely vital. So it'll tell you in detail of where liquefaction could take place, has taken place, may take place in the future. Absolutely vital. So this is the mapping that we're providing now to the people of New Zealand. Subsurface digital models, sedimentary basins. I'll take some examples out of Brad Field's presentation. And again, I'm showing you vignettes. Earlier on, I showed you the immense scope and our mission in New Zealand, and combining it all into a common database. It's a very large job. So I'm going to take now, essentially focus on the sedimentary basins that I started off with. Why? Because that could be the future new revenue stream for New Zealand that the government desperately needs. So here it is, again. Look at it, it's the size of Australia. So that's our exclusive economic zone. Little known about it. Most of it is unmapped. I mean, just basic mapping. Multi-channel ocean floor mapping, unmapped. The geology, most of it is still green territory, but here it is, size of Australia. That's our challenge. And the brown areas are specifically the challenge for potential oil basins. And what is it all about? Attracting oil companies that will invest in New Zealand. Drilling, production, and so on. If the activities by the oil companies take place today, you won't see any results for 10 or 20 years. So it's medium, long-term investment. I'd like to demonstrate to you that this data is available. You can get petroleum data sources from our net, and there it is. It's available to you if you're interested in it. How do we get the data? From seismic reflection and refraction profiling, so echo sounding of the world's crust. And here's an example, I mean New Zealand crust, not the world's crust. And here's an example. We do 2D seismic, that's essentially acoustic echo sounding, and 3D seismic, and then we use other geophysics to probe into the earth. Oil companies and ourselves have built up a very good database in the Taranaki Basin, and there's a Taranaki Basin, and all those are the ship profiles. And if you look at it, there are 2,000 2D seismic lines, certainly more than 20 3D seismic surveys. We have models. We've got the geology in it, again, digital. It's available. It's there. It's free. The result of that data is we can actually build three-dimensional models of the faults, and the red part of the oil source rocks. We can look at that, and that's Brad Field's presentation there. The orange part of the oil source rocks, and then there's migration paths. Just because you find oil source rocks doesn't mean you have oil. Migration paths are where the oil gets cooked up. The orange part also represents a kitchen. That's where the rocks are essentially through natural heat cooked up, and oil migrates upwards. And then you can actually build in 3 dimensions, again, all the migratory paths. And the trick is, now that you've known where oil has migrated, obviously there's oil, that's where you drill. And you drill and you find a dry hole. Why? Because the oil has evaporated. So it's not a complete solution, it's a guide. But anyhow, this is what we do today in 3 dimensions, and actually 4 dimensions, because time comes into it. The oil flow, the cooking of the oil in its source rocks, that's a longer time dimension. I'll talk about shorter time dimensions later on. But it's now available in 3D. I would like now to turn our attention to the remarkable seismic network that we have. It's called GeoNet. That's part of our organization, supported by EQC, and it's led by Ken Gledhill. The GeoNet, first of all, it's integrated. It's throughout New Zealand, and it's a geological hazards monitoring system. And as we'll find later on, it's not only earthquakes, it's tsunamis and remarkable slow earthquakes. We'll talk about that later. It includes research, but mainly it's operational. It's available to you all. You can get it on your handheld and determine immediately where the last earthquake was. We now do location of epicenters automatically. So there it is for you. And the aftershocks are all recorded. So in real time, we monitor earthquakes, volcanoes, as shown by the last rather timid eruptions, Tongariro and White Island, but nevertheless quite scary. We didn't know what it would end up with, but it quietened down. Tsunamis, land stability. Because it's a country of active landscapes I showed you earlier, how stable is it? What's moving? Where is it happening? So we have actually sensors around the countryside, especially towns, that some of them are on hillsides, the whole towns are slipping down. So we monitor that, and we are able to actually give pathways to the origin of this motion, whether it's torrential rain or special hydrological conditions. But we can start giving assurance that we know what is happening under some of these towns. And our end users are obviously emergency managers, obviously scientists, and lifeline utility groups. Now here's something remarkable. In 2000, we had 4 real-time sites. Before that, you'd have to pick the data, would have to be handled, and then it would go on to a landline and then into a center. So in 2000, we had 4 real-time sites connected to satellites. 2012, we have 550 sites. So as you can see how busy we've been by the operational aspects of actually putting the sensors around the country. So it's probably the newest and the best operated network in the world. So GeoNet. We have 52 broadband and 126 regional seismograph stations. So that's our base. We have 180 GPS deformation stations. So we use GPS to look at land deformation and land motion. And of course that affects the cadastral. So then you get down to how accurate is your benchmark? Well, it could have moved. How much did it move? When did it move? So all those questions need to be answered for simple land survey purposes. We have over 240 strong ground motion stations, and we place those in critical areas, Alpine Fault. We had them in, of course, in Christchurch. We've got them in Wellington. We have them all in the urban areas. And then we've built 17 tsunami gauges, at sea level gauges. All of this is coming in real time, 7 gigabytes of data a day, and currently we have on call in our digital database 20 terabytes. And again, look at this last line. It's all freely available. It's all there for you. And then we connect internationally. USA, obviously, especially California, to Europe, Japan, and we're close colleagues of GEMSTEC, it's the Japanese Marine Science and Technology Center, and to Australia. And so this, again, it's a global seismic network. I'd like to go back to this unfortunate event in Christchurch and actually highlight some of the special situations we found there. First of all, 4:30 a.m., 4th of September 2010, the first earthquake, we called Darfield earthquake, magnitude 7. And here is what is quite scary, but I mean, that's the way it was. The epicenter, the depth was 10 kilometers, epicenter 40 kilometers west of Christchurch. So at that time, it was damaging, it was a disastrous aftershocks. We knew aftershocks were coming, and we knew it was a harbinger of things to come. But we didn't really know how big, where exactly would the next earthquake be, what kind of aftershock. That's still a mystery around the world. We can't predict that. Sensors in Canterbury. Before the earthquake, we actually had quite a good network of seismometers around Christchurch. And that actually allowed us to, in detail, determine, I'm going to say map in a sense, but it's 3 dimensions, and not only the February earthquake, but all the subsequent earthquakes up to this July. And I'm going to move through it in detail. Darfield earthquake, surface rupture opened up. Again, all shallow earthquakes. Aftershocks, you can see here all the shock. Then the earthquake aftershocks moved, unfortunately, right around central Christchurch with devastating effect. But why is all this taking place? Why? Because the Pacific plate is incursing onto the Australian plate, hence the Southern Alps. Consequence to that are all of these east-west faults. And I think many of us would be horrified if you removed all the gravel from the Canterbury Plains. You'd be horrified what you see down there. Below the gravel, it looks like a shattered glass plate. Fractures, fissures, faults all over the place. Most of them are older and associated with the collision, the migration of the Chatham Rise, which is up here. But recently mapping in the Chatham Rise, we could see these are active faults, but the lineaments continuing all the way from the Chatham Islands all the way into Canterbury. So these are big global effects on our little country. And of course, we know what the devastation was like over the earthquakes. Toppled buildings, cathedral, gone. But however, I said I'd like to show some special consequences of this. We had strong motion seismometers, and look what these seismometers told us. First of all, we have February, 22nd of February 2011. These are the acceleration in Gs. So the strong motion seismometers tell us this. Acceleration in Gs. If you look at that, the vertical acceleration here is over 2 Gs. I mean, that's enough to launch you into space. So it's 2 times gravity. So you can imagine if you're in that area, 2 times gravity, you're being pushed up, and then, of course, falling down at 2 times the gravitational effect. It's disastrous. Central Christchurch, again, over 1 G, 1 G, 1 G. And so no wonder there was this disaster effect on the buildings. I won't talk about buildings, but fortunately, as you know, we design our buildings to save lives, not to save the buildings. So tragic loss of life, but I think because of the way the structures were built, there was not more deaths from this unfortunate event. So there it is, Central Christchurch. Even in June 2011, more aftershocks. Look at that, 1 G, but already further away from Central Christchurch. So these are some of the remarkable data that we're able to produce. Yes, we do have a tsunami alert map. We're looking at it, we're able to calculate. Here was the earthquake in Japan. Time of earthquake was 1846. On 11th or 3rd of 2011, we estimated the time of arrival. And of course, it was not a disastrous tsunami. We calculated it to be less than 20 centimeters tsunami. But we're now in a position to actually calculate that and warn New Zealand. Now, another event. Many of you may not have heard about slow earthquakes, but our GPS stations show a country constantly on the move. On the right, you'll see the GPS stations. On the left, you'll see one of them in a corral on a farm, very nicely looked after by the population. And we get into slow slip events. What this shows is slippage, actually movement of the surface between 2010 and 2011. And some of the motion that you'll find is of the order of between 0.1, 0.2 centimeters per day. So that's 10 millimeters per day. And the end result, you'll end up with meters of motion, but you never feel it because it's long wavelength. But the effect on the country, the geological effect, is still the same. So you see these hot spots around there as to where the slow motion is taking place. And again, that gives an indication of the stress around these events. Some of them are offshore. As you saw, the last one was quite a large offshore event. And culminating, said in the end, if you look at these contours, culminating in total movement of meters that you are not even aware of. But this is a diagram from research work about a year ago. No, it's more than that, sorry. It's about 4 years ago. Now, what it shows around, here's the North Island. Down here is the Tonga-Kermadec Trench, the Kermadec Trench. So Pacific plate is plunging into it, just the same as a Pacific plate plunged under Japan. And again, the amazing fact about this, it's an absolute analog of what happened in Japan. So the blue is, it's all nice. Blue is actually, the subduction is taking place. It's lubricated. It's going down into the mantle, no problem at all. Of course, some glitches, as you can see in terms of slow motion. There's been meters of motion there over past 10 years. Now, you get down to this area, Wairarapa, Wellington, and you see this red block. This red block is actually jammed in the trench. So the upper block is trying to make its way down, and eventually the two will crack, and eventually this red block is going to move. And it'll be absolutely analogous to what happened in Japan. The size, the shape, of course it's a trench, absolutely exactly the same as in Japan. So we're in, we don't know when, for really a major earthquake there, and tsunamis, of course. We're fortunate that this coast is not populated. Yes, a tsunami could weave its way into Hawke's Bay. We do have models that actually show that. But again, this is brand new science. But it's alarming in the sense it gives us a harbinger of things to come. But again, on the fourth dimension, time, we can't really tell you much about the future. I can tell you what's happened in the past on the fourth dimension, but not the future. And in detail, and again, this is all digital now. This is all in 3 dimensions. So the diagrams that I show you is all available in digital form. But here's what's happening. The plate, this is under Wellington, plunging down, but it's stuck. Stuck at the interface, stuck at about 15 kilometers down. The slow slip zone, gradually, the rest of it is slipping down under the North Island. 60 kilometers is the interface. And sure enough, a few days ago, we had a small earthquake under Wellington, 60 kilometers down. And it's right on the slow slip zone. But this is the real concern. Wellington fault aside, this is a regional event to come. What are we dealing with that? I'd like to give a bit of highlight here for our social scientists. We have a joint project with NOAA, and it's called RiskScape. You can actually look it up, and what, again, on the web, and what RiskScape is. It's an analysis that provides information about the following events. Volcanoes. What are the hazards of volcanoes? There is a model for that. Tsunamis, floods, wind, and of course that's the realm of NOAA. This is where we partner with NOAA. And of course earthquakes. So the challenge for us is enormous. So I'd like to conclude with the following. New Zealand, of course, is a country of active landscapes. And in New Zealand, the earth sciences have to deal with the fourth dimensions. Short term, the fourth dimension, longer term, such as the plate that I showed you. But we have to work in 4 dimensions. And the 3D digital data that we have has to be adaptable for movement with time, because everything changes. And I said the solid benchmarks put in by lands and surveys last century or 150 years ago, you think, well, that's it. I mean, that's it, the geodetic marker. Not so, it's moved. So earthquakes, volcanic eruptions, which are land and submarine, landslides, both submarine landslides will give rise to tsunamis, surface landslides, fault motion, slow slip earthquakes, land elevation subsidence, all have to be dealt with digitally in the 4 dimensions. So that's a challenge for us. We do have the staff. It's going to take time to do it all. Some of it, as I showed you, is already on its way. And the whole idea is to provide this data for the benefit of New Zealand, so the people and the government. But we work for the benefit of New Zealand through the science. And finally, the stacking and multi-source, dynamic digital data. We're going to try to stack now the 4 dimensions of data, one above the other. You could have geology, you could have surface, subsurface geology, you could have recent earthquakes, or all of that. You have to stack so it's available to you to go through it through the complete 4 dimensions. It's quite a challenge. But again, that's exciting for us, and that's what we're working with at the present moment. So thank you.